Good afternoon, everyone. My name is Selvan Thamizhirai. I will give a quick presentation on high temperature materials, where I see high temperature materials being used on aerospace applications, but also give a small insight into the next generation of high temperature materials. So what I plan to do is go through a very quick introduction about myself and my experiences, where high temperature materials are currently used within aerospace systems. And I'll quickly touch on the past, so look over advances over the recent years. And then moving forward, I will break down the technologies themselves into four categories. So first, I will talk about high temperature resins, and then I'll move on to high temperature elastomers, high temperature insulators, and finally, ultra high temperature ceramics. As I said before, quick introduction. I studied in the University of Southampton, reading Astro Engineering, and I graduated in 2016. And between 2016 to 2018, I joined the DENS Engineering Graduate Scheme. And as a fun fact to Akshay's presentation, I was I was seconded out to Airbus with the Zephyr program, so it's definitely relevant. And finally, from 2018 onwards, I joined as a full-time engineer within Dstl, working as a systems engineer with a heavy interest in materials. Where are high-temperature materials used? If you ask this question, people typically give two categories, so I'll break down the two categories, one into airframe, typically leading edges. So high temperature materials are heavily used in all leading edges, most notably the nose cone, and also leading edges on wings. So aerothermal structures heavily use some form of high temperature materials. Somewhere people forget about high temperature materials is in consumables. So in this case, things like materials for the wheels, but also things like O-rings and seals also use high temperature materials. Finally, propulsion systems. If you can ask anyone, everyone will guess high temperature materials are heavily used within propulsion. So they are effectively used everywhere within engine power systems, but also in reheat systems, in this case, the EJ200 exhaust system. I will touch on the advances over recent years. I've broken this into four different categories. So first, the materials technologies themselves, and then I'll touch on academic and then industrial capability, and finally talk about the technology pull from upcoming systems. So first, material technology. There's been a lot of discovery on new and interesting materials over the last 20 years, especially in the realms of ultra high temperature ceramics, but also on interesting systems like graphene and aerogels. There's been a massive improvement generally on materials technologies, but one of the most important things is the reduction of toxicity. So with the world becoming more interested in health and safety, a lot of these materials technologies are very dangerous, especially during its manufacturing phase. So a lot of work has gone into the reduction of toxicity, which directly reduces the cost of producing these materials. Across the world, over the last 20 years, there's been a massive increase in academic capability, notably in China. So a lot of centers of excellence are being opened up by various countries where they invite the best technical minds within materials into the centers of excellence to continuously push research. And there is a renewed interest in designing new materials, which I'll touch on later. Industrial capability wise, a lot, as I touched previously, reduction of toxicity. So a lot of efficient manufacturing is going on to reduce the waste. A notable area where industry is looking into is additive manufacturing, so 3D printing. So it is expected that 3D printing could save on labor costs and production costs. So industry is very much focusing on developing this technology. Finally, technology pull. So over the last 20 years, generally within aerospace, you could say that advancement has been relatively stagnant. However, over the last 5-10 years, there's been a renewed interest in new and future systems. So hypersonic systems, these definitely require high temperature materials, otherwise they can't operate. And also highly maneuverable spacecraft re-entry systems also require ultra high temperature systems, because otherwise they will not survive a high G maneuver whilst re-entry. And notably as well, with the introduction of low-cost airline industry, there's always an interest to reduce the cost of current civil aviation systems. So these technologies and materials could also reduce the cost of current systems. So first, I will break down into my 4 categories on talking about high temperature materials. First, I'll talk about high temperature resin. So what is high temperature resin? A very quick example. This is a picture of a phenolic resin in its physical form. So it's typically very effectively a gooey system, as you can see. And if you're curious, this is the chemical form of a phenol. So what actually is high temperature resin? It's effectively a viscous substance that cures into a rigid polymer. So typically you would have these kind of resin systems paired with some sort of fibers, typically carbon fiber, to form a composite. So a picture that I showed above with the phenolic resin is typically impregnated with carbon fiber, as you can see in the picture, and after it forms a very durable substance, which is called carbon phenolic, as you can see. Broadly, you can split the category of these kind of resins into thermosetting resin, like carbon phenolic, but also thermoplastic resins. Finally, to give a general understanding, high temperature resin systems can survive up to 400 degrees centigrade of operational temperature. So where are they actually used? High temperature resins are used as protective coatings, so you would typically have some sort of a metallic structure, say a tube, and you typically have these sort of systems lining the metallic structure to prevent them from degradation. You can also use them as aerothermal structures, something I will touch on in the next slide. And finally, you can use them as ablative materials. So in the case of carbon phenolic, effectively, it's typically used in spacecraft re-entry systems at the moment. So what they are is, as a spacecraft re-enters, the carbon phenolic effectively turns the thermal energy into a chemical energy and breaks away from the system, the spacecraft re-entry system. So they literally just throw chunks off, and this keeps the internal structure cool, so they ablate. And one of the best reasons to use this is because it's very lightweight compared to equivalent metallic systems. So what is the state of the art? You have cyanide esters. They are very good at the high temperature resistive side, but more importantly, they have very good dielectric properties. So they're typically used in radomes of effectively fast jets. So in the case of Eurofighter Typhoon and Dassault Rafale, use cyanide esters to make their radomes. Bismilabide, BMI, they have very good aerothermal properties as well as temperature resistance. So they're heavily used in the F-35. So if you look at it, an F-35, you could see the weird joining lines. This is because of the way the BMI is bonded on to the aerothermal structure. Finally, you have polydimides, which are heavily used at the moment in automotive industry. So a quick picture showing a exhaust vent from, I believe, one of the new hypercars. So these are heavily used as protective coatings. So you can have a lightweight metallic structure and protect them with polydimide, and that will protect the system. Finally, you have ceramers, which are a very low maturity technology, which show great promise and potentially can be used as they have a much higher thermal resistance than even the rest of these other 3 resins. Okay, so that concludes the resin structures, and I will go on to elastomers. So just a quick showing. So typically you have, what are elastomers? They're effectively rubber systems that can be cured into something very hard. So you probably have seen these kind of thermoplastic tubes at home. They typically use them as quote unquote shatterproof glass structures. But within aerospace, they're typically used in the rubber form, so you could see the seals of the perfluorocarbon in the picture on the left. So what actually are they? So they're effectively polymers which are very viscous. They have very good elasticity, but they have weak intermolecular force. What that translates to in plain English is that it's a rubber-like material. Typically, you have, within high temperature elastomers, you have fluorocarbon families on one side and silicone rubbers on the other. A quick picture showing, again, a different type of sealing system, which is heavily used in the manufacturing of, which is typically used in manufacturing lines themselves. To give an idea of operational range, they have slightly better cold weather properties compared to high temperature resins. So these can typically go from -40 to 400 degrees centigrade. So, like I said, within aerospace, they are used as seals, so typically O-rings. You can also use them as matrix fillers. So if you have a sandwich-like structure with the outside with, say, a high temperature resin, elastomers form as very good matrix fillers to fill the gaps underneath the structure. And similarly, they can also be lightweight foams as well. And finally, one of the more interesting applications of this system is as high temperature adhesives. So typically you'd use some sort of these kind of perfluorocarbon adhesives for bonding some of the materials which are effectively hard to bond on metallic surfaces. And also you'd use these kind of things as flexible components in engines. So some form of, I'm not sure exactly what the material is, but a high temperature elastomers are used in the reheat system for the EJ200. Another picture showing how a O-ring seal looks like. So as I mentioned previously, perfluorocarbon is arguably the current state of the art. They have very good thermal stability. More importantly, they have very good chemical resistance. So these kind of FFKM seals, perfluorocarbon seals, are used within hydraulic systems and fuel systems. You also have high strength silicones as well. They have broadly the same capability as perfluorocarbon, however, they are of slightly lower temperature performance and slightly lower strength. So, and they're also significantly cheaper. So typically some of the non-critical components will have silicone tubes in them. Finally, moving on to insulators. When you think of insulators, you might think of foam insulation, and interestingly, foam insulation is also heavily used in aerospace applications, including both civilian airlines, but also spacecraft. And also carbon phenolics, so you have carbon phenolics as an insulator as well, because they provide an insulating system. But also more importantly, multi-layered insulation, MLI, is heavily used within spacecraft as it's probably one of the best current insulation that you can have. So what actually are they? They effectively are materials with low thermal conductivity, and their main goal is to reduce heat transfer from one side of a system to another. And as I mentioned previously, thermal barrier coatings, so things like carbon phenolics, would be on the outside. So, So a thermal barrier coating is something that's on the outside of a spacecraft system, typically, and aerospace system generally as well. And you also have ceramic foams, so you typically have some sort of a filler within a matrix structure. So ceramic foams would effectively provide a medium which reduces thermal conductivity. More importantly, you also have aerogels. It's this new class of material, and I will touch on in the next slide. And finally, you also have ablative coatings as well, such as carbon phenolics. A quick picture as well. I believe this was, I think it's from the Ariane 5 booster. So the outside, as you can see, uses ceramic foam, as it is a lightweight system that provides insulation. So uses, as I mentioned previously, thermal barrier coatings are probably one of the most common ways you can find insulators within spacecraft. Interestingly, you can also use insulators to build external structures. So typically guide vanes that's sticking outside into the actual airflow, but also things like antenna structures which come out of the and disrupting the airflow typically gets very hot. So you would use an insulator to actually build the system itself. And also reheat system within propulsion units, as you typically don't want the hot gases to interfere with the rest of the propulsion units. And more importantly, this kind of insulator is very important for hypersonic systems and for future windshields. And a quick picture of one of the, I believe it's a ceramic matrix filled system used by NASA Orion spacecraft at the moment, and you could see the tiles being laid on and being bonded to the outside heat shield. So the state of the art aerogels, like I mentioned previously, everyone loves aerogels at the moment because they're extremely light. You could see a picture there, and they're very low density. So these will probably be the next generation of matrix fillers. The current challenge with aerogels is bonding. So at the moment, we don't have a good system to bond the aerogels onto a system. So we have this material, we just don't know how to fix it effectively so it doesn't move around. And also high temperature multi-layer insulation. So best part about multi-layer insulation, as you can see from the Mars Reconnaissance Orbiter there, it's all the yellow structure there, is that it's extremely light, but more importantly, it's very tailorable because it's effectively a textile material. So you just cut it up and then put it around your spacecraft. So final material class is the ultra high temperature ceramics. So this is something that everyone loves. It's been on the forefront of people's minds for about 5 or so years, 5 to 10 years, give or take. And this is expected to massively revolutionize high temperature materials. Unfortunately, because it is very much state of the art, I was unable to find freely shareable pictures. So here's a picture of a testing rig that mimics atmospheric re-entry, and I believe you have silicon carbide, SiC, also known as SiC, which is just inside the plume there. And just a quick photo of how a ultra high temperature ceramic looks like. It is effectively just a lattice structure. So what actually is ultra high temperature ceramics, also known as UHDCs, because that's just too long to say. So it is the overall structure of UHDCs basically looks like normal ceramics. They behave like ceramics when you are within a standard atmospheric conditions and in lab conditions, so you could guess how they look like and how they feel. And these kind of ceramics, especially the first generation, are something called monolithic UHDCs. So, and they're typically borides and carbides. So in the case of SiC, so that's silicon carbide. So you just have silicon and carbon in a structure, and that is one of the first UHDCs. Interestingly, UHDCs have a melting point of over 3,000 degrees centigrade. And modern UHDCs, especially some of the more exotic ones, can survive up to 4,200 degrees centigrade for over 30 minutes. So, and this performance as well can be vastly improved by adding in secondary phases, but also additional coatings as well. So this is part of the reason why UHDCs are currently seen as the next big thing. Quick photo of where UHDCs will be heavily used is in the case of the X-43 NASA demonstrator for hypersonic flight. Uses, they're extremely hard and they're very stiff, just like normal ceramics. And one of its best uses is in, which I'll touch on later, but they have excellent erosion and wear resistance. However, one of the drawbacks with UHDCs is that it has a relatively weak shock resistance, so it'll be a bad idea to put them within a propulsion system directly. However, a lot of work is being undertaken by many different institutions to improve shock resistance so that it's more usable within atmospheric conditions. And because of the high hardness, stiffness, and excellent wear resistance, they are typically used in leading edges of hypersonic systems. So in the case of this artist re-entering of the US Air Force hypersonic demonstrator, all the red bits are effectively lined with UHDCs. So what is state of the art? Is a interesting form of UHDCs. So you effectively have UHDCs with composite, so typically carbon fiber, to improve UHDC characteristics, giving it that shock resistance properties. So UHDCMCs are the current state of the art, and this test piece is one of the biggest test pieces, single piece ever made, and I believe it was produced in 2014 by General Electric for their next generation engines, and is currently going through a myriad of tests. And one of the more interesting forms of UHDC, which is very low maturity, is entropy stabilized UHDC. So in a lattice structure, you might have just silicon and carbon, for example. But then with entropy stabilized, you basically have one carbon atom, one silicon atom, one boron atom, one oxygen atom, whatever. So it's actually quite a complex structure, and however, because of this interesting layout, they have extremely high hardness. They have very good oxidation resistance. However, as you might imagine, this sort of a structure hasn't really been produced yet, so it's extremely low maturity. However, it has the capability to completely revolutionize UHDCs. So final summary, it is a very exciting time for high temperature materials with all this work going on. So in the next 20 years, we could see a massive change in materials for aerospace. So just artist rendering of perseverance. So hopefully the next generation of spacecraft systems could have maneuvering capabilities within high altitude flight, which again could massively revolutionize spacecrafts as well. There's a lot of technology pull from future systems, so that's what's very exciting. And again, a lot of research is currently going on to reduce toxicity and reduce the overall cost of materials as well. And finally, novel manufacturing techniques could also massively improve efficiency and lower cost. And that is everything from me. Thank you very much.
Thank you, Selvan, for a really interesting overview of high temperature materials. I think obviously I've got the privilege of being able to lead off the questions. So the first thing I'd just like to discuss with you is you've given us a good understanding of the various different types of material. I was wondering if you could give us a bit of an insight into how a design team might select the right material for their particular application.
Yes, of course. So first, it's always best to start with a statement of requirements. So really understanding what the material needs to do for their system to work efficiently. So then the design team will sit down, compile these statement of requirements, and then go through a specialist materials team within their company or externally contracted out to then identify a list of suitable materials. And when identifying these materials, it's also important to see where the material could be, say in the case of an aerospace system, 5 years time, because it's possible that even though they're designing now, they're only expecting IOC at say 2035. So it's important to see where the materials development will go. and then obtain test samples. So a lot of these companies that produce all these materials would do test samples, and something which can be tested in-house by the design team to see if it actually fits their requirement, and then if they're happy with the material, then they can order for future.
Okay, thank you. One of the things I was just thinking about when you're talking about the new developments in these advanced materials, firstly, are there any drawbacks? You've talked about their temperature characteristics. What about for things like impact resistance, for example? Are there any significant drawbacks for some of these new materials?
Yes, so in the case of UHDCs, one of the biggest concern is oxidation temperature. So effectively, in the presence of oxygen, oxygen will tend to react with these sort of systems, and it could degrade performance over multiple cycles. So at the moment, UHDCs are amazing for hypersonic missiles because after you fire them, you want to use the system. But in the case of a hypersonic aircraft, there's a chance that after maybe even like three cycles of takeoff and landing, you might have to completely strip the entire system and relay a new set of tiles. So interestingly, that was one of the reasons why the space shuttle had a massive cost, is because after every time it flew, it had to be effectively completely rebuilt. So that's a big concern. And in the case of elastomers, interestingly, so when it comes to these O-ring seals, there's a lot of work being undertaken to reduce toxicity. However, internationally, they're not actually looking to improve the thermal resistance. So I think there is a risk that on the high temperature elastomer side, it might be cheaper to buy these seals, but they may not be up to spec in the next, say, 20 years.
And that brings me on to another question. And by the way, as before, I'll open the floor to questions for attendees as well, and please do put them up in the Q&A. But your mention of O-rings, of course, brings me back to the Challenger disaster and the low temperature properties of some of these materials. Are those requirements still as challenging, or do you see those as having been overcome as well?
So generally, from my work and research, low temperature, the systems that use low temperature subsystems within an aerospace system is typically about -40 or -30. So that is within the spec of current low temperature O-ring seals. However, if there is a demand for systems that's even colder, then that is something that hasn't been captured as effectively as the high temperature side. So there is again a risk that we might turn around for these hypersonic systems and realize we may need a cold temperature component, and that is something that's not being heavily researched because they fit the current requirements.
Okay, no, thank you very much for that. So from the floor, my colleague Simon has asked a question. Are these materials so specialist and enabling that cost is less of a concern than capability?
This is interesting because some of these, especially on ultra high temperature ceramics, they are typically for next generation weapon systems, and only a handful of countries are actively investing in it. So it's only the countries that kind of want the next generation of weapons. So you could probably guess US, China, India, for example, and potentially even us and France. So during these programs, cost is not a concern. However, for high temperature resin structures, and also the elastomers, the O-rings, they're heavily used in commercial aviation. So cost is a significant concern. So that's why a lot of work is being done to reduce toxicity, which means producing these materials would be a lot easier, thus reducing cost.
Okay, thank you. And our chairman, Ross, asked, How has the focus on sustainability affected industry's selection of materials?
Oh, yes. So generally, it seems to have affected the insulators far more because of the fact that they use some form of glass and obviously back in the day, asbestos. I think everyone focusing on high temperature insulators seems to look into the sustainability side far more. However, interestingly, with elastomers, you could argue that lowering the toxicity is because of sustainability, because if you have a bunch of very harsh chemicals that's required for manufacture, then disposing increases cost, but also has a massive concern for future sustainability and environmental concerns. So that's part of the reason why they are reducing their toxicity. However, on ultra high temperature ceramics, that is currently not a concern because they are purely focused on capability, from what I gather.
Perfect. Thank you very much for that, Selvan. That was a fascinating presentation, and thank you very much indeed for answering our questions.